This video is going to show you how to use the work calculated from a graph when problem solving using conservation of energy relationships. Typically when we're using work we do force times distance, but in this example we're going to get that off the graph, so it's going to be a varying force. Here's the example problem. A 2002 kilogram motorcycle stuntman is completing a jump. He lands on the ramp as shown, so my little picture above. He only applies the brakes for 12 of the 20-meter landing ramp before passing out. The graph of his braking force is shown above. What is his velocity at the bottom of the ramp? So if I examine the ramp, I can see that when he lands on the left, he's 10 meters higher than when he ends up on the right. He's traveling at 30 meters per second, and he's going to drive down the ramp 20 meters before getting to the lowest point. And I'm trying to find the velocity at that lowest section. If I look at the graph where he applied the brakes, he didn't apply them at a constant rate, so I cannot use force times distance. Because the graph changes, it's not horizontal, it's got an angle to it, I've got to figure out some other way to find the area, to find the work from this graph to figure out how much energy was transferred away. So to start this problem, I'll start the same way I always do. Sum of the energy at one location plus the work done equals sum of the energy at the other location. So in this case, I'm going to compare the top of the ramp where I know the height and the velocity. Then I have the work of the graph, and I'm going to compare the bottom of the ramp because the problem asks about his velocity at the bottom of the ramp. In the next step, I'm going to look at the types of energies. So I've got kinetic plus potential due to gravity plus the work done by the graph equals kinetic plus potential due to gravity. Now I've got to figure out which of these energies I no longer have. So at the top of the ramp, I look at it and I think, is he moving? And he is moving at the top of the ramp, so I'm going to keep the kinetic energy. Then I'll look for the potential energy. Is he above the other location's height? In this case he is. He's 10 meters above it, so I'm going to keep the potential energy on the left. Then I've got the work of the graph, and that's going to equal, I go through the questions again. At the bottom, is he moving? Yes, I think he's moving with some kind of velocity, so I'll keep the kinetic energy. Is he above the other location's height? In other words, above the top of the ramp? And the answer is no. So I'm going to get rid of the potential energy. This creates my equation. 1/2 mv squared plus mgh equals the work done from the graph, which equals 1/2 mv squared. That 1/2 mv squared is the speed at the bottom. Even though I got 1/2 mv squared on both sides of the equation, they don't cancel out because they're different velocities when I put the numbers in. Now before I put the numbers in, I've got to find a number for the work for the graph. So to find the work done from this graph of force versus distance, I need to find the area between the curve on the graph and the axis on the graph. So in this case, it makes the shape of a triangle, starting from the line and going up to the axis. That's the work, which is equal to the area. Since this is a triangle, I'm going to use 1/2 base times height. So the work is equal to 1/2 the base, which is 12 meters, times the height. And in an unusual way, the height is a negative number because it's below the axis. So it's actually, from this graph, it's negative 10,000 newtons. When I do the calculation, I get negative 60,000 joules. So 60,000 joules of energy was removed. So in other words, work was done on the rider as he went down across that 12 meters. And the remaining 8 meters of the track, he just coasted down. So now I've got a number for the work. I'll finish the math. I'll put in all my numbers. 1/2 2002 kilograms times 30 meters per second squared plus 202 kilograms times 9.8 meters per second squared times 10 meters plus a negative 60,000 joules. So I got that negative from the graph. And that's equal to 1/2 2002 kilograms times the velocity squared at the bottom. When I end up doing all the math, I get a speed at the bottom to be 22.4 meters per second.